Today we'll look at parametric functions. You may or may not have some idea what a parametric function is depending on what kind of pre-calc background you had. Parametric functions are functions that are defined by some parameter. And I'll give you this example. Suppose you threw a ball up in the air, right? And you want to know a path of where it went. It might go up in the air like this and then come back down. And you might be interested in how far it went in this direction. So if you're over here at the origin, that would be how far away it went in front of you. This over here would be your height, right? So your height you might call the y's. But the way that that ball travels is based on something else. And that third parameter in this case happens to be time. So if you had some function, you could define how far it went in front of you in terms of time, and you could define how far up in the air it went in terms of time, which means that every point over here that you would normally think of as x's and y's are actually points that are defined on another parameter. So both the x and the y are based on some parameter. Right? So usually time is a parameter, although it doesn't have to be. I'll bet you've got some experience dealing with parametric functions that don't involve time. And suppose I gave you this. Suppose I said x is equal to the cosine of t and y is equal to the sine of t. Well, as you put in different values of t, in this case, t is not going to be time. T is going to be an angle measure in radians. Okay, and as you do that, haven't you just constructed the unit circle? Where every coordinate on the unit circle is cosine of some value, sine of some value, except in this case the parameter is not time, the parameter is an angle measure. So sometimes it makes it easier to define graphs in terms of parameters than strictly in terms of x's and y's. So here, let's take a look at this example. Suppose I give you x equals 2 times the cosine of t, and y equals 8 times the sine of t. Now, you could put in different values of t to get x and y coordinates, right? If I asked you what this graph looks like, well, suppose you put in t equals 0. The cosine of 0 is 1, multiply that by 2 and I get 2. Sine of 0 is 0, so I'm at the point 2, 0. Suppose I put in t equals pi over 2, right? My x coordinate would be 0. My y-coordinate would be 8 times the sine of pi over 2. Sine of pi over 2 is 1. I end up with 0, 8. Right, you can keep walking around like that. What you'll end up with, and this is not going to be the world's prettiest drawing, but you'll end up with an ellipse that goes long ways like this. All right? So it'll come up at -2 here, and it'll come at -8 over there. All right? So you end up with an ellipse where the major axis is the y-axis, the minor axis is the x-axis. All right, what if I switch things around? What if I said I want to do x equals 8 times the cosine of t, and I want to let y equal 2 times the sine of t? Well, now things are going to be reversed. Cosine of 0 is 1, 1 times 8 is 8, so I'm going to get an ellipse that goes this way, and the major axis now will be the x-axis instead of the y-axis, right? So I'll end up with an ellipse that looks like that. All right, maybe I want to take those parametric functions, those x's and y's that are defined in terms of a parameter, and I want to turn those into rectangular functions, right? Those are the ones that have just x's and y's in them. When I do that, I call the process simply eliminating the parameter. So the question might say, eliminate the parameter. There's a couple of different options we have for eliminating the parameter. So let's say I want to do it for this one here, the x equals 8 cosine t, and the y equals 2 sine t. Because I kind of know where I'm heading with this, let me solve each of these lines for the trig function. So if I divide both sides of that first equation by 8, I'll get x over 8 equals the cosine of t. Over here, if I divide both sides by 2, I get y over 2 equals the sine of t, which doesn't seem impressive until you come up with some function that links the two of them together. So here's something that I know. I know that the cosine of t squared plus the sine of t squared is equal to 1. right? Pythagorean identity, sine squared plus cosine squared equals 1. Well, let's take that cosine and replace it with an x over 8 because we said over here that the cosine is equal to x over 8. So I get x over 8 squared plus, let's replace that sine with a y over 2. And from here, the rest is just simplifying. But you notice that already I've gotten rid of my parameter. I have no more t's in there. So I get x squared over 64 plus y squared over 4 equals 1. There's no t's in there, which would be terrible if I worked at a golf course right now. But here, we have a function that has no t's. This is probably what you learned when you learned ellipses. If you take the square root of 64, you'll get 8. And if you take the square root of 4, you get 2. Yes, apparently this program has a glitter pen. There's my glitter pen. So I should go 8 units left and right of the x-coordinate for the origin, and then 2 units up and down for the y-coordinate. And that's the graph that I made. That's in red up on the top. All right, let's try another one to eliminate the parameter. This one will have a little bit of a different twist to it. So again, eliminate the parameter. Here's my function. X is equal to t plus 1 squared, and y is equal to t plus 2 for the interval of t's between negative 10 and 10. So one of the things that I can do with a function that's in parametric form is I can specify only certain t values, and then I'll produce only part of the graph. So like if I had graphed my ellipses for t values between 0 and pi, I would end up with just the top half of the ellipse. So I can restrict just certain values. Maybe I want to find out when I throw that ball in the air only how it behaves in the first 3 seconds. I can restrict those t values to go from 0 to 3. So here I want this graph, whatever it happens to be, to exist on the interval from negative 10 to 10. So I've got choices. I don't have a nice sine squared plus cosine squared equals 1 like I did in the previous example. So maybe I can find a way to fold one graph or one function into the other. It seems like the x one is more complicated, so I'm going to work on my y's. If I subtract a 2 from both sides, I get y minus 2 is equal to t. And then I can take that y minus 2 and I can throw it in here for t, right? So that I get x equals y minus 2 plus 1 squared, which is x equals y minus 1 squared. Great. What is it and where does it go? Well, we start with t equals negative 10 and we work over to t equals positive 10. So at t equals negative 10, my x's are negative 10 plus 1 squared, right? I'm going back to my original equations up here. And my y's are t plus 2, so negative 10 plus 2. Right? So that produces an ordered pair. Negative 10 plus 1 is negative 9. Negative 9 squared is 81. Okay, negative 10 plus 2 is negative 8. All right, let's see what happens on the other end of this graph at t equals positive 10. I get x equals positive 10 plus 1 squared, which is 11 squared, and y equals 10 plus 2, which is 12. So 11 squared is 121, 12. All right, so what I've really got is I got myself a sideways parabola that starts 81 units to the right and 8 units down, comes up and around, swings like that, and ends at 121, 12. All right, so that's what it looks like, and I can restrict it to just that set of values from 81, negative 8 to 121, positive 12. Writing it that way is a little bit different from writing it with just x and y values, although you can certainly convert back and forth between the two. If we can rewrite these parametrics, I'll bet you we can do some calculus functions with them too. And that's why we came here today. Let's look at some derivatives for parametric functions. It's true that I can take dy dx and split it into two pieces. I can split it up as dy dt and dx dt. So there's a lot going on in this one formula for derivatives. The dy dx tells me how the y's change with respect to x. So if you had that graph of that ball that I threw up in the air, and you wanted the traditional slope of the tangent curve, the slope of the tangent line to the curve, then that thing there is dy dx. Tell me how much the y's change for everything that the x's change. The other two derivatives here, this dy dt up on the top, sometimes you'll see that written as y prime of t. That tells me how the y's change as time changes. So as I throw that ball up in the air, how fast does it go up in the air for every second of time that passes? This thing down here, the dx dt, sometimes is written as x prime of t. That tells me how far it moves left and right for every second that passes. So really, you're looking at a couple of different velocities. You're looking at the velocity that it goes straight up in the air versus how far left and right it goes. When you get done dividing those things, you'll have dy dx. All right, so the derivative of y in terms of x is the derivative of y with respect to t divided by the derivative of x with respect to t. All right, let's take a look at an example. So let's look at x equals t squared minus 5t, y equals t, and I want to find dy dx. So maybe first I'll calculate dx dt since it's sitting right here. The derivative of that with respect to t is 2t minus 5. The derivative of y with respect to t is 1. Now, when you come over here, don't forget that it's actually the y that goes on top and the x that goes on the bottom, even though the way we've written it, the x comes first and the y comes second. Nope. In the formula, the y goes on the top, the x goes on the bottom. Okay. From this, I can actually pull one piece of information out real fast, and that is when t is equal to 5 halves, something weird happens. I get 2 times 5 halves, which is 5, minus 5 is 0. Slope is undefined there. Okay, so if this thing is a parabola, that's where the vertex happens because that's where that thing is undefined for a second as it turns itself around. All right. Let's take a look at another problem that I'm going to sort of wrap around to have 3 different parts. Let's take a look at this parametric function here. And sometimes these parametric functions are functions that you just could not write in rectangular form in any simple way. So suppose I've got x equals 2t minus 2 sine t, and I've got y equals 2 minus 2 cosine t. Now this is something interesting, something kind of interesting. Let's start by doing some derivatives. All right, so the first thing is I want to find dy dx. I could come over here and find x prime of t first, right? The derivative of x with respect to t is going to be 2 minus 2 times the cosine of t, right? The derivative of sine is cosine. Over here, if I find y prime of t, I'll end up with a 0 minus 2, and the derivative of cosine is negative sine. So I end up with 2 times the sine of t. Right, take those two and divide them, but divide them in the right order. Put the y on top, so I get 2 sine of t. On the bottom, I get 2 minus 2 cosine of t. Hey, look, they all have a 2 in them. So I can knock a 2 out of everything top and bottom, and the derivative becomes the sine of t on the top, 1 minus cosine t on the bottom. So this thing is the derivative of y with respect to x. Okay, that's interesting. Suppose that I want to find the slope at t equals pi over 4. So this is not at x equals anything, this is at t equals something. So I want to find the slope at t equals pi over 4. So I should do the sine of pi over 4 divided by 1 minus the cosine of pi over 4. All right, so if we use exact values, the sine of pi over 4 is root 2 over 2. What if I unrationalize this for a second, because I think this will make it easier for us. If I unrationalize this, I know it's not a technical term, I end up with 1 over the square root of 2. So let's do that. Let's leave it in a form where the denominator is not rationalized. Because now if I hit top and bottom with the square root of 2, right, if I hit top and bottom with the square root of 2, I end up with just a 1 on the top and a square root of 2 minus 1 on the bottom. You notice it's still not rational. So here, let's multiply top and bottom by the conjugate. So I'm going to take 1 over square root of 2 minus 1 and multiply top and bottom by the conjugate, which is square root of 2 plus 1. And this gives me square root of 2 plus 1 on the top. And then on the bottom, I end up with a 2 minus 1. So the slope is just square root of 2 plus 1, or you can write it as 1 plus the square root of 2, right? Either one will work. That's my slope. All right, then here's my next question. Suppose I want to find an equation for the line that's tangent to the curve at pi over 4. So the line tangent at t equals pi over 4. Well, I already have a slope, right? The previous example, we found the slope at t equals pi over 4. In order to find the tangent line, I need a point and I need the slope. Well, I already know the slope is 1 plus the square root of 2. I need a point. So to find my point, I got to go back to the original equation and substitute pi over 4 for t. So if I go back to my original equation, I've got 2t minus 2 sine t for the x's. So the x's are going to be 2t, so 2 times pi over 4, minus 2 times the sine of pi over 4. And my y's are going to be 2 minus 2 cosine of pi over 4. All right. And at some point, we might decide we're tired of exact values and start using approximations. So simplify this a little bit. The x-coordinate then is pi over 2 minus 2 times square root of 2 over 2. And the y-coordinate then is 2 minus the square root of 2, because the cosine of pi over 4, square root of 2 over 2. There you go. All right, so the point becomes pi over 2 minus the square root of 2, 2 minus the square root of 2. Okay, I'm going to write this equation out, and then we're going to grab some decimals. So if you remember a point-slope form for a line, y minus y1 equals the slope times x minus x1, I'm going to get y minus 2 minus square root of 2 equals the slope, which we said was 1 plus the square root of 2, that's what we found in the previous part, times x minus pi over 2 minus the square root of 2. All right. Let's throw some decimals in here. I've calculated them so that we don't have to sit here and type numbers in a calculator. For this one, I get 0.5858. Because a 7 rounds up to an 8. On the other side, 1 plus the square root of 2 is 2.414, and then x minus 0.1566. Okay. And then from there, you can take it from there and add values to both sides until you get it solved for y. We should come up with y equals 2.414x plus 0.2078. All right, so there's a decimal point there. That's what we get for the equation of our line. Good. We still haven't figured out what this is, though. So is it possible that I can graph this? All right, let's try to graph this. Let me pull up Desmos screen. It is possible to graph these things in Desmos. Here, I'll show you the setup. If you graph this in ordered pair form, like this, it works. So you're going to graph 2t minus 2 sine t, comma, 2 minus 2 cosine t. And let's do it for t values between negative 10 and 20. Because if you look at the graph that I have on the screen right now, it's not very impressive, right? It just has this one little piece here that starts at the origin. So let's graph the t values from negative 10 to 20. Oh, now something starts to come to life. Let's look at a couple other settings too that might be interesting. For the x's, let's go from negative 4 pi to 8 pi, because then it'll show us some things. So I can type in the word pi. And for the y's, I'm going to come down to negative 1 just because I think it's going to run off my screen if I don't. So go from negative 1 to 10. Actually, I don't even need that much. About 6. Okay. Here it is. Great. What is it? It's called a cycloid. Right? And so if you thought of taking a pencil and attaching it to a circle, and the circle rolls down the hill, this is what you create. You create what we call a cycloid. Right, so it goes up, down, never crosses the axis, and it's not differentiable at these points here because that's where it hits a cusp. If you wanted to graph your tangent line, you can graph that tangent line, and it'll show up real close to the origin, t equals pi over 4. Remember, these are t values, not x values. So when we say that we're going for, let's say, on the circle from 0 to 2 pi, 0 to 2 pi on the t's produce values from 0 to 4 pi on the x's. So this thing hits the ground every 4 pi. Oddly enough, of all the places that are interesting to find pictures of cycloids, Wikipedia actually has a pretty good example of a cycloid. And there it is, right? You see that circle rolling down the hill or rolling along a plane. That pencil that's attached to it is never going to fall below the earth, so it's going to create what we call a cycloid, and that's what it looks like. And now we've created derivatives of these various functions as well.